So today we're going to be thinking about gas particles. To help us visualize what gas particles might be doing at a given temperature, we're going to use this simulation. Now, if we pay attention, we'll notice that the temperature of these gas particles is holding steady at about 27 degrees Celsius. Now look at the movement of the particles themselves. Do they seem to all be moving at the same speed? What's interesting is that they aren't. If you notice, while the majority of the particles seem to be moving at about the same speed, there's quite a few that are moving a bit slower, and then even some that look to be moving faster. So in today's lesson, we're going to dive deeper into this concept, that all gas particles at a given temperature aren't moving at the same speed, and how that can be represented with a graph called a Maxwell-Boltzman distribution. Okay, so my first goal is to make sure you understand what this graph is communicating, what the curve means. I'm going to explain the axes for you to try to simplify things. All Maxwell-Boltzman distribution curves on the x-axis feature a measure of speed. Sometimes it's labeled velocity. So basically this part of the graph, the x-axis, is talking about how fast the particles in the gas sample are moving. And of course, we have meters per second, which is a speed unit. Towards the right end of the x-axis, we would have our faster moving gas particles. And closer to the origin, we would have those gas particles that we saw in the simulation moving really, really slowly. Now, the y-axis I've left unlabeled. You may wonder why. It's because I don't really see a consistent label when I look at a bunch of different Maxwell distribution curves in different textbooks, YouTube videos, and talking to different teachers. A lot of times it'll say probability, sometimes it'll say particle number. So let me just make this as easy as possible for you. When you're looking at the y-axis and you're looking at your curve, the higher the curve goes, the more particles there are at a given temperature. So for example, where the peak of this curve is, which would be somewhere around here on the y-axis, that means there's the most particles out of the entire sample that are moving at this speed, somewhere around 400 meters per second. Now, where the curve is lower, let's say here, that means there's less particles moving at about 200 meters per second. So you can pick any spot on this curve, and the higher that part of the curve is, that means more particles are moving at that given speed on the x-axis. Now, what is with the shape of this curve? Well, you have to imagine that the entire area underneath the curve, everything underneath, represents all of the gas particles in your sample. Right? So you have some gas particles in this part of the curve underneath here that are moving at very fast speeds, but notice it's just a small amount, right? If you go across on our y-axis, there would be a very low number of particles moving, let's say, over 600 meters per second. On this part of our graph, we have a very small number of particles that are moving at less than 200 meters per second. And the bulk of our particles in our sample are right around here, right? This is where the curve is highest, so they're all traveling somewhere around 400 meters per second. And this is what we saw in the simulation. Most of the particles at a given temperature traveling at about the same speed, but always having some particles moving faster and some slower. So that's the basic anatomy of a Maxwell-Boltzman distribution. Now let's talk about how to answer some common questions dealing with these graphs. So the most common question I ask students about Maxwell-Boltzman distributions deal with their ability to understand how the graph or the curve changes when temperature changes. So I'm going to go through a couple examples of that kind of problem with you right now. So remember, our initial curve here represents some gas that's at 27 degrees Celsius, with the bulk of the particles being at about this speed and some moving a little faster and some moving slower, as we saw in the simulation. Now, what if I asked you to draw the curve for the same gas with the same number of particles, but cooled off to 15 degrees Celsius? How would the graph look? Go ahead, take a moment. Imagine how you would redraw this curve. Well, this is the way you do it. The thing to keep in mind when you're doing these new curves for new temperatures is that there still needs to be, no matter what the temperature is, some particles moving really slow and some particles moving fast. You always need to have a bell-shaped curve. Now, the other thing to keep in mind is this point right here, where the curve touches the origin, it always has to touch the origin. You can never have a Maxwell-Boltzman distribution curve where there isn't the far end of the bell-shaped curve touching the origin. The way I like to think of it as this is a piece of string. Now, what I'm allowed to do with the string when I change the temperature is I can pin down this end of the string and simply pull this end out or push it in, right? So I'm going to push it in for colder temperatures and pull it out for hotter temperatures. Okay, so let's look at that 15 degrees Celsius temperature. Because it's a cooling, I would expect more of the particles to fall somewhere over here, right? Because on average, they're going to be moving a little bit slower at a cooler temperature. So I'm going to pin the string down here, take this end, and push it in a bit. Now, how far to push it in is not really important. Usually when we ask these questions, we're not asking you to be quantitative and know exactly what speed the particles are going to be moving at. We just want to know that you understand how the curve would change. So as we push the string in, it gets narrower at the bottom, but the peak is going to rise at a cooler temperature or a slower speed. So your graph would look something like this. Okay? So in other words, now more of the particles are traveling slower. There's still some going really slow, and there's still some particles going much faster. So this is going to be our 15 degree Celsius curve. And again, I want to remind you that there was no math involved with doing this. So two students could submit answers, and one, the peak is here, and maybe on another student's paper, the peak is a little bit over to the left or a little bit to the right. That's not the big deal. That's not what we're looking for correctness. We just want to see that you understand that more particles are going to be traveling at a cooler speed, and overall, the range is going to narrow. Okay, what about that hotter temperature? Well, what I imagine is going to happen is at a hotter temperature, this bulk of the particles, they're going to be moving faster. So this peak needs to shift to the right. But remember, I still need to hold down my string at the origin. So I'm not just going to take this curve and move it over and have it look exactly the same. No, I'm going to hold down my string, pull the curve this way, and I should get a shape that looks like this. Now again, that's not exact, so there's some room for variation there in terms of student answers. But what's critical is that the peak, where most of the particles are, is a faster speed than at 27 degrees. There's still some really slow moving particles. There's still some particles that are moving much faster. So this would be our 40 degree Celsius curve. Okay, let's talk about some finer points and some common mistakes. One point that I think can be potentially confusing is when students see these three graphs, they sometimes find it hard to believe that the number of particles in these three curves is exactly the same. I think that's because the shapes are so different. But in order to help you make more sense of this, imagine two different coffee cups. One is tall and narrow, and the other one is short but very wide. Even though their shapes are wildly different, they both hold about 8 ounces of your beverage. So when you look at these three curves, even though this one is really tall but narrow, and this one is really wide but much shorter, and of course the original curve is somewhere in the middle, I assure you that the area underneath each of these curves is exactly the same. Because when we heat up a sample or we cool it off, we're not making more molecules or reducing the number of molecules. So that area under the curve needs to be consistent. Now, to figure that out mathematically, you have to use some calculus, which we're not going to be doing in any of our high school chemistry classes. But I hope this example with two different shaped coffee mugs that hold the same volume gives you a sense of understanding when you're looking at these very different shaped curves, but thinking to yourself, they have to be representing the same exact number of molecules that we had in our original sample. To conclude this video, I thought it would be good to show you the most common incorrect answer to questions where students are asked to redraw curves on a Maxwell-Boltzman distribution representing a gas sample at different temperatures. And that incorrect answer usually looks like this. And it's a very easy and understandable mistake. Typically what students do is they say, well, when the sample gets hotter, I want to take the same shaped curve, because it's the same group of particles, and just shift it over to the right. Or if the temperature drops, they take the same shaped original curve and just move the whole thing over to the left. So I hope you understand, based on my previous explanation, why these do not provide accurate representations of what gas particles are doing. For example, with the red curve, according to this graph, none of the gas particles in the hotter sample are moving at very slow speeds. You'll see that it sort of hits zero somewhere around 300 meters per second. But when we look at those simulations, this is not what we see. We see that even in really hot samples, there are some very, very slow moving particles. So in conclusion, this sort of mistake is common. It doesn't accurately represent what happens when we heat up or cool off a sample of gas particles. You always want to use that string technique where you're just pinning this end down, stretching it out, or pushing it back in, which will always change the peak and will always change how wide the graph or the curve is at the bottom. I hope this video was helpful for you. Please feel free to leave a comment or a question down below. Have a great day.